Hello and welcome to our video on the reactions in alkanes, alkenes, and alkynes. Today we'll be covering over some of the common reactions that alkanes, alkenes, and alkynes will undergo. So the first type of reaction that we're going to discuss for the alkanes is a combustion reaction. Please refer to the previous video if you're confused on the type of reactions. We covered combustion reactions in more detail then, but in the way of overview, basically a combustion reaction, you have a fuel, which is usually in this case going to be the alkane, and then you supply a bit of energy, which might be a spark as it's an exothermic reaction, and then the fuel reacts with oxygen. And if it's complete, so a high yield association is knowing that if it's complete, it'll form carbon dioxide and water. However, if it's incomplete, it'll form carbon monoxide and water, or it could also form just carbon in the form of soot, and you would just represent that as C. In your tests, especially if you get a question on complete combustion, write out the alkane plus the oxygen with carbon dioxide and water as the products and just balance it that way. That's pretty straightforward. If you get a question on incomplete combustion, there are two ways you can do it. You can either write carbon monoxide and water as the products, or just plain carbon and water and then balance it afterwards. There are two more important things to remember. So a visual representation is if when you turn your Bunsen burner on in chemistry class and you open the hole and then it's got a nice blue flame, that's complete combustion occurring because you have excess oxygen or enough oxygen to occur. If you have incomplete combustion, or you close a hole, you get that yellow sooty flame, and that's where this carbon and this carbon monoxide come into play because you're getting that incomplete combustion. Alkanes can also undergo substitution reactions. So you may recall from the previous video, a substitution reaction is when one group displaces another in a larger compound. In an alkane, the number one thing to remember is that alkanes are relatively unreactive species, right? So substitution reactions occur in alkanes only in the presence of free radicals. This is usually like a halogen free radical. So that might be like the Cl- or Br-, so on and so forth. So we have an example in the next slide, but one thing I need you to remember is these reactions require a high amount of energy. So you need to break these bonds apart, and that usually comes in the form of UV light. The UV light doesn't actually break apart the alkane, it actually breaks apart the bonds present in not the chlorine, just the halogen in general, these divalent halogen molecules, and they create free radicals. These free radicals then go and then attack the alkane if you like, and then substitution reaction occurs. So this is a pretty common alkane substitution reaction. So we have pentane, which is your alkane, and then we have chlorine, which is our divalent halogen of choice. When we break up this bond, and we'll do that by supplying some high energy UV radiation. So always remember, alkane substitution reactions will need some large energy input, right? When we do that, what we'll get is the results of that will be 2 chloride free radicals. And you may recall a free radical is the atom with an unpaired electron in its outer shell. So I've just represented that unpaired electron with a dot, right? So these free radicals are now ready to attack this alkane. So let's pretend they're here. Let's do them one at a time. So that chloride free radical is now in position. So this chloride free radical will preferentially like to bond with this carbon way more than this carbon likes to bond with this hydrogen. So what will happen is you basically get an intermediate bond forming here, and then that bond kind of gets weaker and weaker, and that hydrogen shoots off. So the result is you have 3-chloropentane and hydrogen chloride, which bonds with the other free radical here. So in summary, when you're given an alkane substitution reaction, so in a question you might get the alkane and you might get the chlorine and then told to find the products, right? Basically what you're going to do is always remember that one of the halogen atoms joins the alkane and one of the hydrogens joins with the other free radical to give you that product and the haloalkane. So now we'll go over some of the reactions that alkenes can undergo, and for the first one it's combustion. there's not too much of a big difference between combustion reactions in alkenes compared to alkanes. They're much the same. The concepts of complete reactions producing carbon dioxide and water, and incomplete reactions producing carbon monoxide and water, or carbon and water, are much the same. One thing to remember is make sure your formula is right. Especially, you may be given in a question, you might be given, say, pentene forms undergoes a combustion reaction. Write the actual reaction. So make sure you know how to write the formula for pentene. So the formula is CnH2n. So the formula for pentene would be C5H10, and yeah, so on and so forth. So the first type of reaction that an alkene can undergo that an alkane can't is a hydrogenation reaction. Basically, what we're doing is it's kind of like an addition reaction in where hydrogen is added across the double bond of an alkene. And in this way, we can actually convert alkenes to alkanes through these hydrogenation reactions. You need a high temperature, usually about 150 degrees Celsius, and a platinum catalyst to undergo these reactions. And the importance of the platinum catalyst cannot be stressed enough, and you'll see why. So we have ethene undergoing a hydrogenation reaction to form ethane, and I'll show you the mechanism in which this occurs. So this red block here kind of represents my platinum catalyst. Look, it's not entirely important that you understand this mechanism, but it's just a good understanding to be able to appreciate it. So this is ethene approaching from the top. I'm not going to draw the hydrogens in, but essentially what is happening is the platinum catalyst kind of breaks apart this bond, and one of the carbons is able to bond directly, actually, to the platinum catalyst. This other carbon here is now free to bond with the hydrogen, because remember, we supplied a high temperature, we've broken up this hydrogen, and now that's ready to bond there. So in the next step, we have hydrogen, we have another hydrogen, which is now bonded, we have another hydrogen, we have a carbon, which is still bonded, and then we have two hydrogens here. Basically, what's going to happen is this will kind of turn, and then another hydrogen can sneak in and link with that, and that will give you your final product, which is ethane. Long story short, the high yield associations are that ethene or any alkenes can be hydrogenated to form their counterpart alkane. You need a high temperature and a platinum catalyst to do this. So alkenes can undergo three types of addition reactions: a hydrogenation reaction that we just covered, an addition reaction with a halogen, and in the next slide we're going to cover an addition reaction with water. So halogens can undergo an addition reaction in which so a halogen can be diatomic, so Cl2. With an alkene, it'll undergo an addition reaction in which the alkene accepts both of those on either sides, so both of the halogen atoms on either sides. You may recall that with an alkane, it wasn't an addition reaction, it was a halogen substitution reaction in which it would only accept one, and then there would be another composite byproduct, which in our example was hydrogen chloride. Click back to an earlier point in the video or a couple of slides before to refresh your memory. However, we'll cover the addition reaction with the halogen. So there's a brief mechanism that does occur. We'll split up this bond again. So what's going to happen is this bromine is going to attack here. The first bromine is actually going to disrupt this carbon bond. This carbon double bond, I might just correct myself. And what it'll look like is it'll form a bond with both carbons instead of this bond here. And that'll give this bromine a slight positive charge. What will happen then is, so that's one bromine dealt with. What will happen then is this second bromine will come. This second bromine has a negative charge. Will come and attack this carbon kind of inferiorly or from the bottom side and create a bond here, disrupting this bond here. So thus, you only have this carbon bonded with this bromine, and you get this final product, which is 2-dibromoethane. So in this way, you can see that, I'll just clear this again. Long story short, you can see that the bromine was added across the double bond, so one on either side. And then both of the bromine atoms were accepted, unlike the alkane substitution reaction, in which case only one was accepted. Don't really worry too much on the mechanism. You can, it helps you understand it, but it's not essential that you memorize it. Another key detail to remember is that this is a common way that alkenes are differentiated from alkanes. So this bromine will give like a nice amber color, especially in aqueous solution. And when you react it with the alkene, this product is colorless. So the reaction goes from amber to colorless, and thus this is a confirmatory test for the presence of the original product, which is an alkene. So up until now, we've been talking about ethene and other symmetrical alkenes, and they're symmetrical because they look the same on either side of the double bond. However, I'll propose like a nice little problem for you. If I were to have so if I were to have propene, I've drawn propene here, and if I were to make it undergo an addition reaction here, there's actually two ways in which this can add. So in one of the ways, the hydrogen would add here, and in the other way, the hydrogen add here, and the chlorine would obviously take the other position. So I'll give you the two possibilities. So in one of the molecules, so I'm going to call this number 1 and this number 2. So when propene undergoes an addition reaction with hydrochloric acid, it can either go the addition on the top, where the chlorine is added in the first position, or the addition on the second, where the chlorine is added in the second position. Now, how would I determine which of these, so option number 1 or option number 2, is more likely to occur? Because we have two possibilities. You would think that it would be 50-50, you'd get equal amounts of both, but that's not entirely the case. And a rule that you need to know is Markonov's rule. He postulated that when you add a protic acid, so H and then X, so X could be chlorine, bromine, so on and so forth, that could be hydrochloric acid, hydrobromic acid, and so on and so forth, to an asymmetric alkene. That's the key here, an asymmetric alkene. So when that's done, the hydrogen will actually add to the carbon with the most hydrogens attached already to it. So if I draw propene up again, and I add the hydrochloric acid, so we look at the double bond. So this carbon has 1 hydrogen, this carbon has 2 hydrogens, so the hydrogen is going to likely attach to this carbon, and the chlorine is going to attach to this side. So to give you something that looks like this. Instead of the second option. So that was number 2 in the previous example that I drew. Okay, to show you this reaction in a little more depth, I should just add it's Markovnikov's rule and not what I said earlier. I have a simple reaction occurring between pentene and hydrogen bromide. It's not entirely essential that you understand this, the mechanism behind it, or memorize it. Just have a good appreciation of it. So when we apply enough energy, so there's 2 electrons present in the single bond in hydrogen bromide. When you apply energy, it'll split, and the more electronegative bromine will actually take the electrons present in the double bond. So the net result of that would be H plus And since bromine has stolen the electrons that it always wanted, it'll be Br minus. Now the first step of the equation is hydrogen needs to attack this double bond because it currently has no electrons. So as you can imagine, it's going to attack the most electron-rich area around it, which in this case would be the double bond. Now, I'm going to draw some dots. It can take electrons and form a bond with this carbon or form a bond with this carbon. And that'll give you two sets of different kind of molecules. So in the first instance, it would look like this. I'll draw it out for you. So I've drawn out an intermediate step where hydrogen has just attacked and broken apart the double bond. So now we'll unpack that in a little more detail. So I'll pick out the hydrogen color, so it'll be blue for this time. If it attacks this carbon and takes electrons from this carbon, it'll bond here. And what it will do is, since the other carbon no longer has the same amount of electrons, so the electrons that were present in the double bond are currently used to make a new carbon-hydrogen bond, this will form a slightly positive charge, and we call that a carbocation. The opposite happens if it attacks the other electron, so the other carbon, so this carbon, for example. So if the hydrogen attaches here, the other carbon will become a carbocation because the bond or the electrons that we use to make the double bond are no longer present. They're now used to make a new carbon-hydrogen bond, which makes the other carbon which leaves the other carbon with a slightly positive charge. So I'll rub that out. Now, big old bromine is a bully, and he will come and attack this positive charge. So bromine will bind here, and bromine will bind here in the respective positive charges. Now, you would think that option 1 and option 2 would happen in equal ways in nature or equal amounts in nature if you were to actually do this experiment. However, that's not entirely the case, and that comes down to the carbocations that we were talking about. So I'm going to draw them back again. It just happens so that the positive charge of the carbon with the positive charge, or the carbocation, is most stable when there is a large electron-dense group around it. And electron-dense groups are usually around alkyl groups. So option 2 is going to be a lot more stable than option 1, as it's only got some hydrogens around it. So think of it this way. The carbon with a lot of groups will accept a new group, which is a bromine. The carbon with a lot of hydrogens will accept a new hydrogen. And that is what's kind of happened in this reaction. So hopefully you've understood the mechanism, and now we'll go through the actual reaction now. So pentene reacts with hydrogen bromide. So the hydrogen could either attach to this carbon or this carbon, right? So we get two different products. We get 2 bromopentane and 1 bromopentane. So which of these do you think we would have more of? I'll have to give you a brief moment to just reason out which and why. Yep, so hopefully you should have come to the conclusion of 2 bromopentane. That's because, I'll clear the page now. This carbon here already has the most amount of hydrogens compared to this carbon here, which is 2 versus 1. So the hydrogen will attach here and the bromine will attach here. Another way of remembering is, conversely, the carbon with more groups attached, which is this carbon, will attach the bromine, and then the converse is true. The other carbon will attach the hydrogen. Whatever floats your boat, just remember the rule. So those are most of the common reactions for alkenes. We'll have some rather good multiple choice questions that'll give you the products and then ask you to find the reactants, and vice versa. Give you the reactants, ask you to find the products, and also revise some of the flashcards as well that we've created. But now we'll head on to alkynes. So with alkynes, they can also undergo combustion. Again, this is relatively straightforward. If you understand the combustion mechanism for alkanes, for alkenes and alkynes, they're both the same. So the rule for alkynes is they can actually undergo pretty much for your case in year 12 chemistry, number one, they won't really give you questions on alkynes to start off with, but if they do, they undergo the same reactions as, say, an alkene does, but instead of this double bond breaking into a single bond, the triple bond will break into a double bond, and I'll show you some examples in the next couple of slides. So as I said, one of the reactions that alkenes and alkynes can both undergo is a hydrogenation reaction. Again, similar to the alkene hydrogenation reaction, you need the platinum catalyst and about 350 degrees Celsius of temperature to get this going. So I'll draw the platinum catalyst here. As you may recall, the ethine, in this case, will actually directly form bonds with the platinum catalyst, which results in the abolishing of this bond here. With enough energy, you'll get the breakdown of this hydrogen to form individual hydrogens. These hydrogens are then able to attack the carbons on either side, and obviously this would rotate. Feel free to flick back to the previous slide when I go through alkene hydrogenation reactions to understand the full mechanism. But the only difference is, in the alkene hydrogenation reaction, you had a double bond become a single bond when the alkene directly bonded with the catalyst. In this case, you have a triple bond becoming a double bond when the alkene reacts with the catalyst. So your final product is going to be ethene. Then, if you let the reaction proceed, it can happen once more, and then it can undergo an alkene hydrogenation to form ethane. So main takeaways, exact same premise, so it's the same mechanism, but for the alkyne hydrogenation reactions, it goes from a triple bond to the double bond, and then from the alkene hydrogenation, it goes from the double bond to a single bond. But in the same case, you get hydrogen added across. Okay, very similar to alkenes, alkynes can also go in addition reaction with halogens such as chlorine gas. So in a similar vein, you need high UV light and usually a lot of energy, and usually a high temperature as well. This will break the chlorine-chlorine bond and form two free radicals. And you may recall, free radicals of chlorine look like this, and they are the chlorine atom with an unpaired electron in its outer shell. So essentially, one of these free radicals will actually attack the triple bond or of the ethene here, and it will create a intermediate such as this one here. So the chlorine will actually bond to both of the carbons here. Now you don't need to understand the mechanism, but just know the fact that this configuration is actually extremely unstable. So we've used one of our free radicals to actually attack the triple bond. The other one is going to attack from the behind this carbon here. So essentially what you'll get, or what is the official name for it, is a trans dihalide, which is this structure here. Now, this can then undergo another alkene addition reaction if you have excess chlorine. So these two can react and give you the tetrahalide there. So it's a bit different to the alkene addition because there's no hydrogens here. They're replaced with chlorines. So you're kind of starting off with a trans dihalide, and then they undergo another addition reaction with the halogen of choice, which is chlorine in this case, to undergo the tetrahalide transformation. Similarly, I should also just add that alkynes also undergo, if they are asymmetric, so I've used two symmetric examples, both ethene. If they're asymmetric and you have an addition reaction, they also follow Markovnikov's rules, but instead of the double bond going to a single bond, obviously, as I've stated before, the triple bond will go to a double bond.